Okay, so let's consider the case of a general capacitor like we've looked at before. So I'll have just these two irregular conductors like this, and they will be each given equal and opposite amounts of charge. So let's say that this one is given some positive charge, and this one is given some negative charge. Like this. And what I want to think about is what would happen if I then connected the two conductors together, right? So if I took this situation and I just attached a wire from one to the other, well, positive charge would flow along this wire from the positively charged one to the negatively charged one. Or we could have negative charges flow the other way. Which one is which doesn't really matter, but the key is that there would be a current. And so in that current, we would have positive charges, let's say, moving from a higher potential to a lower potential, so there would be some change in energy. So delta U would equal Q times delta V. Okay, so there'd be a change in energy in that situation because there's some potential difference and some charges flowing along it. So let's figure out what that would be. Okay, so if we take this relationship, and we also recall that in a capacitor, Q equals C times delta V. All right, and the capacitance doesn't depend on anything else. It's just a property of the geometry. The shape of the two capacitors tells us what that will be. Well, let's say that we imagine charging up the capacitor. So going from no charge on either of these to piece by piece, removing a little charge from one and adding it to the other until they end up at the final amount of charge. Well, the energy that it takes to move some individual piece of charge partway through that process is going to be equal to the potential difference, which I'll just write as V, which is going to depend on how much charge is present already. Okay, so that'll vary as we go. For the first electron that I move from one to the other, there's no cost to it. It takes zero energy because the two conductors are both neutral and they're at zero potential. For the last one, I'm going to be dragging that electron across the entire amount of charge of the two conductors. So that amount of potential difference is going to change as we go. Okay, so du is going to be the potential difference at some charge times whatever amount of charge it is that I'm moving. Okay, so dq is that little bit of charge. And then if I want to find the full charge, or the full energy on the whole capacitor, then I'm going to have to integrate that. So integral of du from the very beginning to the end, which is going to be the integral of v of q dq from q equals 0 to q equals the final charge, which I'll call capital Q. All right. Well, I know how the potential difference is going to depend on the amount of charge. I have a formula for that right here. Okay, so v of q, which is the potential difference, is going to be equal to q over c. Or, in our case, because we have little q is the amount of charge that's present partway through charging, little q over c. So then I'm going to have integral from q equals 0 to big Q of q over c dq, which we can integrate easily. That's going to be 1/2 q squared over c from 0 to big Q, so that's just going to be 1/2 big Q squared over c. Okay, so the energy of a capacitor is just that, 1/2 q squared over c, or we can use the relationship that defines the capacitance to write this in a slightly more common way, 1/2 c times delta v squared. All right, so what this tells us is that the amount of energy that is stored in a capacitor is going to depend on the charge and the potential difference according to this formula. So capacitors store charge. Capacitors also store energy. And one of the ways that we use capacitors in practice is as a way to store energy. Instead of using a battery, you can use a capacitor. Okay, so what is good and bad about using a capacitor in this way? Well, the benefit of using a capacitor to store energy is that the amount of charge and discharge on the capacitor can be built up or removed very rapidly. So they charge and discharge rapidly. Typically you can charge a capacitor in much under a second, depending on what all the other details are in the circuit. And that's usually really good. Often we want to have a large amount of energy that is delivered very fast. But there are some downsides. So one is that the delta V is going to change as we go. So when you take a charged capacitor and you first start discharging it, you'll get a very large amount of charge flowing in the first little bit, and then later it's going to not be as much as you go. So you'll get a lot of energy at first, but then it'll kind of trail off as it goes. Also, not only the potential will vary in that way, but also the amount of charge will vary in that way. So in particular, the discharge is not uniform. Okay, so capacitors are really good in some circumstances for this purpose, and they're less than ideal in other circumstances.